are in causal inference and statistics. It never scrolls the first time I grab that, don't know why. We're in this book right here. And we are in chapter 4, dealing with counterfactuals. And we're in a section of chapter 4 that is dealing with mediation. And we went through a lot of stuff about mediation in the previous video, which is right here. So it may pay to watch that. But now we are on question 4.5.2. So we're considering the following structural model where we have a expression for y, which is a function of m, the mediator, and t, the treatment, where m is additionally a function of t, right? I mean, that's what it is to be a mediator. Maybe I should just clarify that really quick. So we'll go back to this example. Not that the question that we're working on has to do with this DAG or this example, but just hopefully it makes sense here. Let me find a better one here. Let's go here. Okay, so we have that t, or that, okay, so we had that y was a function of m, which is represented by m in this arrow, and t here, so just ignore all this top part, anything dealing with w. And then we additionally had that m was a function of t. Okay, so that's kind of what this is looking like, right? So we're going to use the basic definitions of natural effects, natural direct effect and natural indirect effect, to define or to find the natural direct effect, the natural indirect effect, and the total effect. And these equations we'll see as we go along here. So I didn't publish them here. And then we'll repeat this, assuming that the error terms are correlated. Okay. For NDE, this is equation 4.46 in your book, and it's right here. And so what we are doing is we are finding the difference in the outcome under two counterfactual scenarios. One, where treatment is there, 1, or treatment is 0, while holding the mediator constant at the value it would assume if treatment was 0. Okay, so again, for more clarification on that, go back up to the mediation example. We go through that in a little bit more depth. But, so we just churn through the math here, and we get expressions for y under both scenarios. Okay, and then we just apply our counterfactual to anything in the parentheses. Okay, so I've broken this big expectation term up into a bunch of little ones, just because, I mean, why not? You don't have to do that. And then we just push these counterfactuals through. So anywhere where we see an m, we give it the value that we would get under m equals 0. Okay, and anywhere where we see a t, we give it a value of 1. Okay, and we do that across the board. What is the value when for m naught? So this means the value for m when t equals 0, right? M is given a little counterfactual there. Well, if t is 0, right? Well, then this becomes 0, and I think that we're supposed to assume that the error term is on expectation 0. So that means that m is 0 when t is 0. Okay. So, and similarly, when oops, wrong one. Well, okay. We'll get to m1 here in a little bit. So anyway, so that m right there becomes a 0. That t becomes a 1 because that's what it's supposed to be. Okay, and we do that across the board. We see that we have 2 zeros here on the right-hand side, and the expectation of the error is, I believe, supposed to be 0. So all of this equals 0, so it drops out. And then over here, we have 0 plus beta 2. Beta 2 times 1 is just beta 2. Plus the expectation of the error, which again is supposed to be 0, so we should just get beta 2. It's natural direct effect. All right, so now for the natural indirect effect, this is a slightly different expression. Now we are holding treatment at 0 because we want to see the effect of the mediator, basically. And then we vary the mediator from the value it takes on when t equals 1 to the value it takes on when t equals 0. Okay, so it's just the same order of operations that we've already done. We break this out into its little itty bitty expectations, and then anywhere where you see a t, you give it a 0. No t there. Here's a t, so it becomes 0, so on and so forth. And anywhere where you see an m in this side, you give it the value m1, and anywhere on this side, you give it m0. Well, we already saw that for the NDE that m0 is just 0. Okay, so that becomes 0. Well, what is the value for the mediator when t equals 1, which is what that symbol right there represents? M when t equals 1. Okay, well, we can go back up here. Well, if t equals 1, well, then we have 1 times gamma 1. And again, the error term is supposed to drop out under expectation. And so when t equals 1, m is gamma 1. Okay, so we put gamma 1 in there. Okay, so here's m1, and so here's our expression for m1 under t equal 1, right? That's that counterfactual. So we push that through and we just get gamma 1. The error drops out because the expectation of the error we're supposed to say is 0. And so then we get the expectation of beta 1 times gamma 1. These are supposed to be fixed values, right? There's no variability in the parameters. And so the expectation is just them themselves. Now, finally, for the total effect, we have, so there's two ways that we can get the total effect. And the simple one, if we're lucky enough, is just the sum of the NDE and the NIE, two values that we already found. Well, how do we know if this one applies? Well, if we have a linear system with no interactions. Well, we know that that's the case here because, so interactions or variable-specific effects. And if that doesn't quite make sense, go back to the previous video. But we see that we have exactly a linear system here. There is no nonlinear terms in here. So that means that we can use the basic formula NDE plus NIE. There is an alternative, which is NDE minus NIE sub R, and we don't have to do that here, luckily. We may in the next problem, I'm not sure. In fact, I believe we do. So we'll deal with that then, but we also dealt with it in the previous video. Okay, now for the next part, we're going to repeat all of this, but we're going to assume that the error terms, UY and UM, are somehow correlated. Well, I don't think that it actually matters, at least not in this case. And the reason I don't think it matters is, so somebody should correct me if I'm wrong, but if I'm thinking through this correctly, I think that you just run the exact same math here. And the reason being is because in these counterfactuals, kind of the whole idea is that we're assigning hypothetical values to the system and then holding everything else as it was under observation. And so what is everything else? Well, it's the error terms. And so I don't think that it actually matters that the error terms are correlated. I think that's accurate. So anyway, if you think that that's wrong and you have a better explanation, then please share it. Okay, yep, we'll call that good.